All right, today we are going to be talking about optimization. So the first thing we are going to start off with is a theorem. So this is called the second derivative test. So suppose that f is continuous near c. If f prime of c equals 0 and f double prime of c is greater than 0, then f has a local min at c. If f prime of c equals 0 and f double prime of c is less than 0, then f has a local max at c. So we're going to test the local max and min values of f of x equal to x cubed minus 3x plus 2. So the first thing we are going to do is find our f prime of x, which is going to be equal to 3x squared minus 3. Plug in 0 so we can find our x values. We get 3 equals 3x squared. 1 equals x squared. So x equals 1 and negative 1. 2, we're going to find our f double prime of x, which is equal to 6x. So if we plug our negative 1 value in, we get negative 6, which is less than 0. If we plug our 1 value in, we get 6, which is greater than 0. Therefore, what we can say is there is a local min at f1, which is equal to 0. If we plug our 1 value back into the original equation, and then there is also a local max f negative 1, which is equal to 4. So now we're going to go over some guidelines with optimization. So you can think of this as steps, but these are definitely suggested in order to find the values that you are looking for optimization problems. So the first is going to be draw if needed. So sometimes people will ask you to find fencing around a certain area, and so that would be useful to be able to draw out to visualize. Number 2, so you are going to find a constraint equation and your objective equation, which these might seem a little confusing right now, but we're going to go over it when we do all of the problems. So 3 is you are going to take the derivative of the objective equation and you're going to want to find the critical points. So kind of what you've been doing in other ones. 4, we are going to do the second derivative test. So we can make sure that if we're looking for max, make sure that's what we're properly looking for, or if we're finding a min. And then 5, we are going to plug it back in, and from there we should be able to find our values really easy, whatever else we're looking for. So now we're going to go into some important formulas that you should have on hand or at least have memorized when you're doing these problems. So we're going to split them into 2 categories. So one on the left side, we're going to have volume. And on the right hand side, we are going to have surface area. So these are just your common ones that you're definitely going to see when you're doing optimization problems. You have box. The formula we use is V is going to be equal to L times W times H. So length times width times height for a box. A sphere is going to be V equals 4 over 3 pi r cubed. Cylinder is going to equal V equals pi r squared h, so height. And then for a cone, we have V equals 1 over 3 pi r squared H. And then for our surface area, for box, we have 2LW plus 2LH plus 2WH. For a cylinder, we have 2 pi r squared plus 2 pi rh. And finally, for a cone, we have pi r squared plus pi rs, and S is slant. It stands for the slant. So for example 2, we're going to build a rectangular pasture for our pet turtle. He loves to roam, so we want the area of the pasture to be 20 square feet. How should we build our pasture to minimize the amount of fence needed? So the first thing that you're going to want to do, or that you can do if needed, is let's go ahead and draw a picture. So we know it has to be a rectangle, and we know, let's just give our x and our y for our side and our width. So we know that our area, x times y, we want it to be 20 square feet. So this is going to be our constraint equation. So y is going to be equal to 20 over x when we move our variables around. But our objective equation is going to be the perimeter. So that's how we're going to minimize the amount of fence needed. So perimeter is going to be equal to 2x plus 2y. And then we are going to go ahead and plug our y into that. So we get 2x plus 2 times 20 over x. To simplify that, we get 2x plus 40 over x. And then to make our life a little bit easier when we do derivatives, we will do 2x plus 40x to the negative 1. So again, this is going to be our objective equation that we are going to be using, and then up here the area is going to be our constraint equation. So this was kind of like number 2, which I forgot to mention. So for 3, we are going to find the derivative. So p equals 2 minus 40x to the negative 2. Now we're going to go ahead and plug in 0 for p so we can get our critical values. What we end up with is, if we multiply x to the negative 2 on both sides, we get 2x squared minus 40. Divided by 2, we get x squared minus 20. 20 to both sides. We get 20 equals x squared. Flip that around a little bit. We get x equals plus or minus 20, but we are going to want it to be positive, so that is going to be around 4.5. So the next thing we are going to do is we're going to go ahead and check and make sure that this is a minimum value. So it's just to do a check to make sure we're going in the right direction. So take our second derivative test. We get 80x to the negative third, which is going to be greater for 0 for any x that we plug in. So it is a min. And what is our min? It is going to be that x is equal to about 4.5. Now we plug it back into the original equation that we have, which was that constraint equation. And we are going to get y equals 20 over x. Plug our x in, 4.5. And our y is also equal to about 4.5. So funny enough, so now that we have our x and we have our y, we know what they should be. And funny enough, it actually equals out to be a square. So that is going to be the minimum value that we need for our pasture for the turtle. Next, we have example 3. We were hired by a company to design a can for a new product. The can will be a cylinder, and the volume of the can must be 100 cubic inches. What should the dimensions of the can be if we want to use as little material as possible? We go ahead and draw out a picture so we know what we're looking at. So this is going to be our cylinder. You're going to have an H for height. And right here, make it red so we see it, is going to be our R. That's just a little bit hard to see, but you get the picture. So Now that we have that, we have our number 2, which I kind of already did the constraint equation first, but this is part number 2. So we have V equals, which is what we're given, our volume up there, V equals pi r squared h, which we know we want it to be at going to equal 100. And from there, we can get our h, which is going to be equal, if we move stuff around, 100 over pi r squared. Next, we're going to have our objective equation. So that's going to be, we can use surface area, which we know surface area of a cylinder, if we go back a couple slides, is 2 pi r squared plus 2 pi r h. Let's go ahead and plug our h back into this equation. But I'm going to make it a little bit easier. I'm going to take 2 pi out of both. And so 2 pi multiplied in parentheses by r squared plus rh. 2 pi r squared plus r multiplied by 100 pi r squared. And then if we reduce it, we get 2 pi to r squared plus 100 over pi r to the negative 1. The derivative of this equation is going to be equal to 2 pi, and we have 2r minus 100 over pi r to the negative 2. So now we can take this, set it equal to 0, and let's go ahead and find our critical values. We divide 2 pi to both sides. We get 2r minus 100 pi r to the negative 2. We're going to multiply r squared to both sides. We get 2r cubed minus 100 over pi. We divide by 2 to both sides. We get r to the third minus 50 pi. We just change it up. We get r to the third equals to 50 over pi. So r is going to be equal to 50 over pi 1 to the third, which is roughly about 2.5. So we take our surface area, we get the second derivative, which is going to be 2 pi 2 plus 200 pi times r to the negative third. And no matter what number we plug in, it is going to be greater than 0. It is a min. And what is a min? Our r that is about 2.5. So finally, we take our r, we plug it back into our original equation. So we get h equals to 100 over pi times 2.5 squared, which is roughly about 1.6. So we have our r and we have our h. Example 4, a rectangular bin open at the top is required to contain 128 cubic meters. If the bottom is to be a square at a cost of $2 per square meters, while the sides cost 50 cents per square meter, what dimensions will minimize the cost? So we're going to draw a box. So this is going to be our height of the box. And remember, the box is going to be a square at the bottom, so we will give it s times s. So what do we want for this equation? We want s squared, which is going to be using the bottom, multiplied by h to be equal to 128. So if we want to change this equation around, again, this is our constraint equation, we get h equal to 128 over s squared. Now, for our cost equation, this is going to be the equation that is our objective. So what do we know? So we're going to say, 2, which is going to be the $2 per square meter, times s squared, plus we're going to take half of and half is because of the 50 cents. So half of 4SH. And so 4SH is just 4 times the side times the height. So that's going to be our cost equation, because again, that's going to be, because you have to separate the bottom from the sides. So that's where we get those two equations from. And again, the bottom is found, the area is found by S squared, which stays right there. We need meters, we need square meters. And then this is just going to be our 4 times S times H, because that's all we need. We don't need to worry about the top. So now what we're going to do is just simplify it. So we're going to take that H that we found earlier and plug it in. So 2 times S squared plus 2S, plug in H, and we get 128 over S squared. And the 2S is from the 4 times the S multiplying by that 1/2. Then to simplify it some more, we get 2S squared plus 256 over S. Next, we are going to find the derivative of our C equation. So 4S minus 256 over S squared. Let's find our critical values for S, or I guess our critical value for S. And then we're going to multiply S squared to both sides. We have 4S to the third minus 256. Divide 4 by both sides. We get S to the third minus 64. Then we get S to the third equals 64. And then S is equal to 4. We can do the second derivative test, which C double prime is going to be equal to 4 plus 512 over S to the third, which doesn't matter what S is equal. It's going to be greater than 0 no matter what. So it is a min. Lastly, we are going to plug it into our original equation. So we get H equals 128 over 4 squared, which is just equal to 8. So we know what our H is, we know what our S is, and we know that those have to be a min. So with those, we are able to minimize the cost of the bin that we are looking for. Example 5. A solid steel cylinder is to be produced so that the sum of its height h and diameter 2r is to be at most 3 units. Find the dimensions that will maximize its volume. So finally we have a maximize one, yay! Alright, so the first thing we're going to do is just again draw a picture, and we kind of already have seen what a cylinder looks like, but we're just drawing it again. So that's h, and then again right here is going to be r, which is our radius. And so we are given for our constraint equation that h plus 2r has to equal 3. So if we move the equation around, h is going to be equal to 3 minus 2r. And so for our objective equation, it's asking to maximize the volume. So the equation of our volume for a cylinder is pi r squared h, which is going to be equal, when we plug h in, to pi r squared 3 minus 2r. Which if we want to multiply this out, we get 3 pi r squared minus 2 pi r to the third. Now we're going to take our restraint equation, find the derivative, which is going to be equal to 6 pi r minus 6 pi r squared. Plug in 0, and then we can go ahead and we can solve for our r value. So what we get, 0 equal to 6 pi r, 1 minus r. So we get 0 equal to 6 pi r. Therefore, r would equal 0. And we get 0 equal to 1 minus r, where r equals 1. So we actually have two values that are possible, which we'll go into which one is which in a minute. But first, we just want to double check and make sure that we have a max. So do our second derivative test, which is equal to 6 pi minus 12 pi r, which is going to be less than 0. So it is a max. Yay! Finally, what we're going to do, so when we plug our 0 into our volume equation, we get 0. When we plug 1 into our volume equation, we get pi. So we know that R1 gives us our max, not 0. So now we're just worried about 1. So what we can do is now plug it back in, where h is equal to 3 minus 2r. So we get h is equal to 3 minus 2 times 1, and we get h is also equal to 1. So we have our r value that we know we need, we have our h value, and we know that it is going to maximize the volume of the cylinder. Our final example is example 6. So two non-negative numbers are such that the first plus the square of the second is 10. So find the numbers if their sum is as large as possible. So we are going to be maximizing for this one. But at first, so this is where we really don't need to draw it, but we're going to need to find the equation. One where we're going to, or the second one, which is going to be our constraint equations. So we're going to have, let's name some x and some y. Those are going to be our two non-negative numbers. So it says if we have x plus y squared, that is going to be equal to 10. So if we are going to pick whichever number we want, we can do x equals 10 minus y squared. That's going to be our constraint equation. So because we know our objective is look for the sum, we're going to have a big S equal to just x plus y. And then we can go ahead and plug our x in. That's going to be 10 minus y squared plus y. Now we can get the derivative of our s, which is negative 2y plus 1. Plug in 0 so we can find our critical number or numbers. Then we get y is equal to 1/2. Then we do our second derivative test, which is equal negative 2, which is less than 0. So it is a max. Now, the last thing we're going to do is take our y value, plug it back into the original equation. 10 minus 1/2 squared is going to be equal to 39/4. So with our y and with our x value, that is going to be the largest possible sum for the two non-negative numbers that we are looking for in this example. So thank you for watching this video, and stay tuned because there should be a part 2 just going over a few more optimization, because optimization at first can be a little tricky, but once you start doing them more and more, it'll get a little bit easier and you'll be able to find a rhythm so you can solve them quicker.